So let's go to CAD exercise 6. Okay. So I will try to finalize everything in CAD exercise 6 as much as possible. So mostly, all of you, most of you have said that CAD exercise 6 was quite straightforward. So I will not go through too much in detail. So this is instruction of non-overlapping clock generator, right? And we also use the standard cell to build this non-overlapping clock generator. And we also set the simulation setup for standard cells. And if you press F11, then you can hide this left navigator. So anyway, so we set up like this, but it is only applicable for this PDK, GPDK45. So if you simulate standard cells in different process, for example, like Global Foundry 22 nanometer or TSMC 65 or 28, the procedure may be different. So it is not the golden standard for simulating standard cells. But for this PDK, we can simply build like this way. So simulation of non-overlapping clock generator. So I built like this, and let me open this simulation window. Okay. So for non-overlapping clock generator and this switched cap, so I simply put NMOS minimum size C1, other NMOS C2, and for comparison, I also put ideal RC low pass filter here. So let's say we will use it later. 0.1 and C1. Let's say at this moment we have set 1 picofarad and 1 picofarad, and clock, as mentioned, 1 megahertz, 1 mega ohm for the R, and VDC, it was 0.5 volt, right? VDD1. And variable T trend. Let's run only 2 cycles of clock. And when you plot this clock and P1, P2, then you can see that those are operating quite nicely. And if you zoom in this little area, you can see that its rise time is 1 nanosecond, and our digital circuit is quite fast, less than 1 nanosecond, response time. You can see that there is a non-overlapping window, right? It is measured as a 58 picosecond, and so it does not, turn on at the same time with certain amount of non-overlapping window. And the same thing also happens here. 59 picosecond. Maybe you can rearrange, then 58. Roughly measuring it. So non-overlapping window is 58 picosecond. And I also prepared theoretical calculation of first order switched capacitor low pass filter in Python here. So this is more or less simply copy and paste of our course GitHub from the Python. You can copy and paste, or you can do the git clone. So anyway, this is a track and hold transfer function and sample and hold transfer function. Equations are there. And I also prepared this more accurate equation of switched capacitor 2. and switched capacitor 1 is there, and RC low pass filter is there. So let me erase everything and set it as a 1 picofarad. Okay. Then I just set it as RC low pass filter, 1 mega and 1 picofarad. Then you can see that it looks like this. This is because 1 over 2 pi factor. So you can, I guess you can divide by non-pi pi like this. Then you can take 1 megahertz, right? So if you increase by the factor of, let's say, 10 and 10 mega ohm, then you can set 10 kilohertz. And I prepared ARPA. So for we have for loop here. When I equal to 1, then ARPA is equal to 10 to the power of 0. That goes to 1. And the scaling factor is 1 over 10. That goes to divided by 10, and so on and so forth. So you can see that 10 kilohertz, 100 kilohertz, 1 megahertz, and 10 megahertz. So we have completed this one. So here in this case, we can print here R and C as R ohm C as a farad. Then 10 mega ohm and 1.59 picofarad. So let's say we have CRC like 9 pico, and RRC is 10 mega ohm. And let's test this in terms of AC analysis. Let's say 10 megahertz, which is 10 times higher than the sampling frequency. Close this one. And if you set it as a -3, then yeah, it is 10 kilohertz, right? So it runs correctly. And C1 and C2 to build a first order switched capacitor low pass filter. Then I prepared the equation here. So this one is same equation as this, Fs over 2 pi here, and C1 over C2 in hertz. And let's run it. Let me comment out this one. And it goes like 10 times larger, right? So at this moment, let me set it as a, let me see. So maybe we can increase this one. No, it should be decreasing, right? Yeah, then if we set C1 as a 100 femtofarad, then you can see that switched capacitor low pass filter cutoff frequencies are aligned. Then we can print C1 and C2 values here. Then C1, C2, 100 femtofarad. So C1, let's say 100 femtofarad, and C2, because we set C2 as equal to C, this is because we want to model this one as a R, and we want to keep this and this capacitors as the same. So let's say C2 is set as a CRC. Okay. And calculate the theoretical gain for 10 kilohertz input to 10 kilohertz cutoff frequency. This is simply 3 dB, right? For first order low pass filter in 3 dB 3 dB frequency is the cutoff frequency, which is exactly same as a pole frequency. So 3 dB in magnitude dB scale is a 3 dB, and in linear scale, we can calculate this one. Also prepared. Yes. So if we apply, for example, which is related to the next question, so the linear scale, it is 0.7. So the 3 dB means that it is the power is half in power domain. So in linear domain, we take square root. So this is exactly same as 0.7. So let's run the simulation for burst order low pass filter. So transistor widths are given as indicated, and we take 10 kilohertz, amplitude is 100 millivolt with 500 millivolt DC bias as this. DC bias 100 millivolt, and we need to assign here F in 10K. And supply voltage 1 volt and a capacitance. Okay, so here let's run the transient simulation. In this case, we want to take a look at until 2 cycles of F in, and we don't need to run AC. In this case, let's run it. Yeah, you can see that its simulation speed is a bit slower. So this is because there is a big difference between 10 kilohertz and clock 1 megahertz, which is 100 times difference. So this simulation setup is measuring all the transitions of clock. The data are all saved for all the 1 megahertz clock transitions, but our F-in is 100 times slower. So this is the reason why the simulation speed is quite low. I mean, slow. So if we plot this one, then let's plot input and intermediate term, voltage, and this is a switched capacitor output, and this is a RC output. So for the RC output, let me divide. For the RC output and the SC output, switched cap output, for the lower values, it follows quite nicely, right? But for the high values of input, you can see that there is some discrepancy here. It cannot follow quite well. So initial values, these are our settling moment. So it requires some amount of time to settle down. So even if you run larger number of cycles of F-in, you will see the similar situation, because it follows quite well for this region, RC, which is a theoretical expectation. This is SC here, right? So this is because our porosity cap formed by here, RC, and here, RC, which is our own low pass filter. Cutoff frequency is so lower, such that its speed is limited. So in this case, we can also check by looking at these 3 waveforms. Oh no, sorry, not RC, SC. And you can see that for low input value, here, this node quite nicely follows the principle of track and hold operation. So for clock is high, then let me see here this way. For V1 is high, then this intermediate node, net 25, must follow V in. So it follows V in quite well. For V1 is low, then it should be following to V2 because V2 will be turned on after some non-overlapping time, and it should follow quite well V out at C, right? But as we move on to higher values of V in, you can see that it is not following quite well because of limited bandwidth. And yeah, so it should be touching V in, but it's barely touching it, right? But this is some problem and problematic situation that most of you have faced during the simulation. So the solution was reducing the capacitance value C1 and C2, right? So in this case, maybe we can thinking about reducing C or the R, starting from RC and increasing R. Then RC low pass filter is let me keep this one as it is. Then the RC low pass filter is set as a 10 kilohertz, and SC case is a 100 kilohertz. So in this case, we can even further reduce this one to 10 femtofarad. So in this case, we can see that if we set C1 and C2 10 femtofarad and the C2 as a 159 femtofarad, then it sets quite well for the SC low pass filter. So for R, it should be 100 mega ohm, which is quite a large value, but at this moment, let's not think about too much. And 10 femtofarad, and the CRC, which is equal to C2, is 159 femtofarad. Okay, and let me also run, let me first run the AC simulation. And dB, and for minus 3 dB. So yeah, it is 10 kilohertz still. So now we can run transient simulation. So for speeding up this kind of transient simulation, you can see, in this case, you can check this lever. So what does it mean is that conservative is the most, conservative is the most accurate simulation setup for the transient, and this lever is less accurate than conservative. So it collects more sparse data. So this is a lever, and for the conservative, it collects more dense data. And the simulation accuracy for calculation method is more accurate. But for getting some brief understanding, let me run for lever setting. Let's run the simulation. You can see that it's a bit more faster. And for this kind of waveform, if you want to refresh it, you don't need to re-clicking all of these things one by one. You can simply press Ctrl R, then this update. Now you can see that it follows quite well. This 1, 2 input, and also switch to cap, even if input value is high value. Of course, in low value, definitely follows quite well. So let me overlap this SC and RC, and let me delete this one. Then you can see that both of RC low pass filter and SC low pass filter matches quite well. And when we measure peak-to-peak value, which is 140 millivolt, as we expected here, if we apply 0.2 volt peak-to-peak, which was input because I applied 100 millivolt amplitude, then the peak-to-peak value is 0.2 volt peak-to-peak. So the output is expected as a 141 millivolt. Okay. So let me comment out this part. And yeah, let's go and move on to the next section. So this is the last section, right? PSS and PAC, running it. So you need to remember to make sure there is no frequency component when you run PAC, and make sure there is a 1 signed, assigned here, a PAC magnitude. So you run transient this case, and PSS auto calculate 10 conservative, yes, apply. For the PAC, let's run 1K to 10 mega, maximum sideband 0. So we have to run AC simulation also. Okay. So we can plot AC response. Let me delete this window. And for the PAC, you can select spectrum dB and this one. Yeah, so you can see that it has almost no difference between PAC and RC. Of course, there is some jumpy thing at high frequency. So to have a look, you can run more points. Let's say 100 points. Okay, if you refresh it, you see that it shows the theoretical expectation of sample and hold. Of course, if you run more data points, then you can collect more of this. So let me also realize this ARPA in simulation setup for running parametric sweep. So let me define ARPA as a 1 here. So in this case, we are controlling C value. So C2, there is a CRC here. We divide by ARPA. Okay, for the quick verification, let's run ARPA for 1, 10, 100, 1000. And to check these values, let me see. Oh, what is wrong? Normally, oh no, sorry, not this one. Should be 1, 10, 100, 1000. And you can go analysis, show or sorted. And you can see that the list of parametric sweep you will run. So 1, 10, 100, 1K. Let's run the AC simulation first. And go back here and press for R. Let's remove this one, Control R. Oh, it doesn't work. Then we can plot this one again. Yes, we have to save it to output here. And let's run parametric sweep. Sometimes it stucks like this. So it runs only for 1 and 100 case. So then in this case, let's run manually. Let's change it to append and ARPA equal to 1 here, for ARPA equal to 10, 100, and 1000. then if we set 3 dB, this, you can see that it is very nicely set. 1K, 100K, 1 mega, and 10 mega. And in this case, let's run PSS and PAC. So for ARPA, let me set it as a 1. Let me first run the PAC PSS. Okay, so for PAC dB and plot this one. Okay, let's save it to output like this. And for the append mode, we can simply run for 10. We will compare this output with theory. So let me save this data. So CD6, let's say 1. Okay. So for ARPA 10, let's run it. Yeah, so if I move this one toward here, and you can see that its sample and hold operation is shown, and it has discrepancy between this RC and SC. This is as expected in previous lecture slide. Let me also save this one. SB, okay, and ARPA 100. Okay. Now you can see that its bandwidth is exactly same as sampling frequency, but it cannot extend over the 100 megahertz because it is theoretically blocked by sample and hold operation. Okay, for alpha equal to 1000 and run it. Yes, similar. Okay, then using this data, let's move on to this plot. So for at this moment, let me comment out. I was running the previous one. So this is same Python script as you can find from our course GitHub. The answer for correct sampling theory is sample and hold, not track and hold, right? Sample and hold goes to more higher attenuation to the sampling frequency. And the switched capacitor filter works in sample and hold operation. So let me first import CD6 data, let's say 1, and this one, 1. And here I set it as a omega C as a low pass filter cutoff frequency. I set 10 kilohertz. Yes, then you can see that it has almost no difference between RC low pass filter and simulated switched capacitor filter. As we have seen in this simulation setup. And for second one, definitely you can see that it has a discrepancy because of calculation error as in previous lecture. But you can see that its sample and hold theory matches quite well to the simulated switched cap filter for this region. And for third one, increase to 1 megahertz. And if I run it, then you can see that now it has a smaller attenuation because of this RC low pass filter, but otherwise it matches quite well to the theory. And if we increase the cutoff frequency even higher, then you can see that theoretical low pass filter cutoff frequency is here, but until this frequency, there is almost no attenuation. Then it follows quite well to the theory for the sample and hold. This was expected, right, for the CAD6. And I believe all of you answered. It was quite straightforward in terms of this way. And since we have 5 minutes left, so let me also go through this Switched-Cap filter equation of this one, the last one that we analyzed in terms of Z domain. So here I have collected SC low pass filter 2, and let me comment out for the low pass filter 1. Then this one calculates SC low pass filter 2 of equation is calculates on this. So fs over 2 pi, fs over 2 pi, and log ln, which is natural log, and c1 over c2 here. We can also rewrite c2 as a 1 and c1 over c2 here. So the equation is basically same. And unfortunately, we need to do some manual tuning of this case. So for example, our equation has a C1 at the numerator. If we increase C1, then maybe we can increase cutoff frequency. For example, if I set this way, it's too much. This way, or maybe this way. Then we can align this 10 kilohertz, right? But we have verified already in previous RC low pass filter equation 1 that it matches quite well. So let me try to align this one, 80 kilohertz. So in this case, let me see. Let me go back to here and maybe increase this. Okay, nice. Okay, then you can see that 100 kilohertz is quite nicely aligned. So we can use C1, C2 values, 14 femtofarad. Let me set ARPA as 10 and C1, where's C1 here? 14 femtofarad. And otherwise, looks correct. Okay, then let's run it. Let me change it to replace. Okay, now you can see that it matches quite well each other. So if I save this data as CAD6, let's say 22. Let's say. For version 1. Let's say version 2. And it should be 100 kilohertz. Let me see for version 1, dotted line, and what about this? No? Wait, what is wrong? Let. Okay, then you can see that the dotted line here is a RC low pass filter, and the version 2 aligns and follows quite well to the theory of RC low pass filter, right? For easier plotting, we can move this plot to later. Still not quite well shown. If I increase this one to -2. Okay, nice. So you can see that these black dotted lines are quite nicely matched to cyan here, V2, right? Except for sample and hold theoretical expectation, and the red line deviates a bit here. So this was the discussion of lecture 7 and lecture 8 about calculating exact transfer function of switched-capacitor filter and CAD exercise 6. Okay, so this is it for today's lecture. So we will have a short break and we will continue to the quiz for 5 minutes.
One small question about CAD. Is it always that when we have a digital part also, we need to have separate grounds?
Separate grounds. Ground? Okay.
Is it always that it need to be like that, or is it something that, like, why it's happening? Why, when if we use the same VSS to the digital part and the analog part, it fails?
It may fail not because of fundamentally different mathematical calculation. It may fail because of noise coupling from digital circuit to analog circuit. That can happen. So mathematically, there's no difference.
Okay.
So if you can make sure both of them has a separate, clean, very clean ground, and if you connect them all together, then theoretically, mathematically, there should not be any difference. But it may be failing the operation if there are a lot of noise coming from digital to analog circuit. That can be possible. So it's not mathematically different.
Yeah.
Yeah. Thank you.